I have a doubt, because at the beginning, when we decided to organize this conference, we spoke about 3 lectures, then they became 2, and I couldn't decide what I wanted to cut. Moreover, okay, I must tell immediately that my background is the one of a physicist. I got my degree in physics, and only later I got a PhD in mathematics, and finally I ended to teach in an engineering school. So I liked very much the physicist point of view. However, I could pull a little bit your leg, the legs of the physicists, talking a little bit following the idea presented by Professor Russo. In my opinion, everywhere in physics, people studied a problem like this one. For Professor Vulpiani, who was not here yesterday, I will tell that we have a sponge, you have a porous medium, full of a fluid. And the fluid can flow from one pore to the other. The fluid is compressible, the matrix is deformable, and you want to study how, for instance, in a one-dimensional problem, the flow, how the water is flowing through the upper surface of this body. Okay. Now, I believe in what Professor Russo is telling. That is, in general, somebody had the good idea for deducing, starting from a variational principle, the right equations for describing such a phenomenon. Then a physicist gave an interpretation, or the author himself gave a physical interpretation to the terms of the equations, and after some transmission of the information, say after 2-3 rewriting of the book, then the old variational procedure, which is rather mathematical, is lost, and people is left only with the equations which are more or less appropriately used. This phenomenon, I will not tell the source in order not to cause problem to people. This phenomenon we have observed in a textbook in a famous grande école in France. In a book of hydraulics, now you find copied in a very bad way some words which for sure come from Middle Age. There is a definition of a fluid which is terrifying. Okay. Sorry? I will give you then privately. Now I want to tell you that I woke up one morning, and following my physical inspiration, I decided that MF is the apparent density of the fluid filling this sponge. Epsilon is the vertical deformation of the sponge. And P0x is the initial pressure of the fluid inside the sponge. I got a vision, and for physical reasons, I need these terms. This is pre-stress, the linear terms. These are quadratic terms. This term is describing the interaction between the fluid and the solid. And then as I am not a mathematician, so I ignore the homogenization results of Pierce-Seppicher, I tell you that two pores, close, are interacting one with the close one, so you cannot deform one pore without having a reflex of deformation in the other pore, or you cannot change the pressure of the water in one pore without deforming the closed pore. I could speak, say, 10 minutes, and if your face is not clever enough and if you are not understanding, I could tell you that you are missing physical intuition, because to me this is very clear. Yeah?
Sorry. You are writing a sort of free energy for this system.
This is the deformation energy for the body. You have the sponge.
Yes, yes. Okay.
No, I don't want to use the free energy because I'm afraid to be wrong. So it is in a sense. You have the energy related, you have a cube of this sponge. This cube is deformed, the solid matrix is deformed by epsilon. So epsilon means how it is elongated. And the water fluid content of this cube is described by MF, which is the apparent density. Okay?
But those gradients are not functions, are not squares. Usually the free energy is sort of above free energy.
No, but here you have grad epsilon square. Grad mu, grad epsilon.
The square includes the gradient.
So you...
Gradient epsilon.
Yes. Yeah, it is unhappy notation. So you have a quadratic expression for deformation and a quadratic expression for the gradient of deformations. But grad epsilon, you should consider, we are dealing with a one-dimensional problem, so grad epsilon is a scalar. It is the derivative of epsilon along the depth of this sponge. Okay? So, with this energy, you calculate first variation, but you know, I could tell you that this is, by the way, this is already an integration. Delta Px is the applied force at the top. So I could do as engineers are doing. I could tell you that you have the balance of force at a depth x of this body. You have contact forces from the bottom. You have a contact force at the top. And this first equation is balance of force for this slab of x. Okay? While this one is in a without m dot, because m dot is difficult, so I can hide at the beginning. I could say that you have the balance of force for any fluid part in this slab, okay? And m dot and m dot second are related to dissipation, Darcy type flow. So we want to describe a kind of transport of fluid with respect to the solid. And this phenomenon, in this phenomenon, which is quasi-static, so you don't have any kinetic energy, no acceleration, the only time-dependent terms are related to the dissipation phenomenon. By the way, this is a problem very important in engineering applications, because very often engineers build something on a porous medium, and when the building is built, after 2 years, the building is sinking, you know, sometimes even not regularly, because they didn't calculate how the, yeah, but it happens very often. Okay, but you know, as I know that Angelo is suscettibile, permaloso. Okay, I will tell them. I will not pull his leg too much. So we got this equation in a mathematical way, calculating the first variation of an energy, second gradient energy, and the point shown by Pierre Seppecher before is crucial. This system is highly inhomogeneous at a certain microscopic level, which is the level of pores. By the way, with Pierre yesterday on the beach, we did some experiments. If you place your foot on the sand wet, you see immediately the area around your foot becoming dry, because you get a sudden loss of fluid content there. The second gradient energy is required in this region because when you apply, and then I will behave as a physicist, but this idea I like very much, you apply, with the foot you apply a force on the solid matrix. The grains of the solids with zero energy can rearrange, decreasing the voids. The fluid can freely go out of the voids with few dissipation, but the layer is very small, so this energy can be neglected.
Where appear here the fact that the sand is a Newtonian system? Where appear this formula is the fact that it's Newtonian?
Newtonian, you mean dissipation? Non-Newtonian is what?
No, he means as a fluid, but I think you consider
So
it as a
the
solid.
sand doesn't behave like
No, we are considering a compression phenomenon. So the sand, roughly speaking, is a solid. Only if you have liquid. No, I mean, if you have a sample of sand and you apply compression forces, you can model it as a solid. Okay, but maybe the example was not happy.
But then, if you didn't have the second gradient, what would you see when you put your foot? What do you expect?
Without second gradient, you have.
The water remains there.
No, the water goes out immediately.
Goes out.
You have infinite speed. The water, I will show you. What happens is nothing is opposing to your pressure, and mathematical equations show you a singularity. So you have a Dirac delta of something. For instance, density is suffering what I showed you yesterday. Okay, so if you study this equation, I can tell you these are the classical deformation terms with the good derivatives. These are the higher gradient terms, those who take into account the fact that at the layer where you apply the force.
To be sure that I understood correctly, can you switch back to this? So this equation is the minimum of the previous energy.
No, it's not exact. You need a Hamilton-Rayleigh.
What is the relation between this and the other?
The first variation of this is equal to the dissipation of Darcy flow. So the principle of least action modified by Hamilton-Rayleigh. So the first variation of this energy equals the first variation of dissipation potential. Okay? So the terms here are coming from standard deformation, which is not giving any contribution, relevant contribution on the layer where you apply the force and the fluid is coming out. These are the terms which account for the interaction between closed pores, which is negligible usually and becomes relevant at the boundary where flow is going out, and this is Darcy-Brinkman dissipation terms. We dissipate not only with the velocity but also with the gradient of velocity, so you have these terms. Okay, and yesterday I skipped a little bit this. When you integrate by parts using a second gradient model, you get all boundary conditions you need. And of course, instead of telling you that I got it integrating by parts, I could tell you that this is standard boundary condition for stress. So you get maybe you could think about the standard pill argument of Maxwell. You have the force at the top, which is balanced, external force, which is balanced by the contact force, pressure-like or stress in the solid. Then this is a general chemical potential condition. You say that the fluid which is coming out goes in a reservoir which has a fixed chemical potential, so in this way you are fixing the boundary condition. Then you can say that nothing is opening the pores at the top of this sponge. So if you think about the pantographic system Pierre Sepéchet was describing before, you have a double force which is opening or closing the first module of the pantograph. Think about an action which is opening the pore at the top. So you could inject in this high pressure in the first layer of pores. Okay. You say that there is no double force applied there, and there are no capillary actions on the fluid at the top. Then you have impermeability condition at the bottom, and then you have for the fluid, and then you have that the solid sponge is not moving at the bottom. With these boundary conditions, you get, okay, I want to be precise, this solution with these waves is clearly dirty because these waves are the effort which the numerical code is trying to do for approximating a Dirac delta. And this is the best the numeric code can do. Okay, so the singularity of classical Terzaghi was a German, Austrian engineer. The best way, by the way, Terzaghi flow of the fluid in a porous sponge is exactly what, by definition of Angelo yesterday, is a standard transport. It is the transport controlled by the good equation of Fick type. Okay, and this discontinuity here between initial conditions and boundary conditions is causing a trouble. With the regularization of this, with introducing second gradient materials, you get a capability of the upper layer of the sponge to resist to the external actions, and instead of having this regularized Terzaghi solution after this 1/1000 non-dimensional time, you get this much more realistic profile for the consolidation problem. So The problem of studying how a sponge is consolidating is a rather difficult problem, especially because of lack of knowledge of the right boundary conditions. In the paper which I have written with Pierre Seppecher and Angela Amadeo, we have proven that the boundary conditions available in the literature, and I could find more than 200 papers, can all be gathered when they are right under the general scope of a Hamilton-Rayleigh principle with suitable dissipations at the boundary. So there is Dereksiewicz, Safman, there is a huge amount of persons who spend a lot of time trying to get the right physical intuition for finding boundary conditions. These problems, in our opinion, can be easily solved if you choose the right variational principle and you calculate first variations. So I will use the time I am left to try to tell you quickly some of the ideas we needed to use for finding the right boundary conditions we have used both in the problem of consolidation and are needed if you want to study shock waves inside a porous medium. This is not a meaningless problem from the physical point of view, because it is well known that at least in some oil reservoirs full of high pressure fluids, there are shock waves which may be caused by inappropriate behavior of the engineers trying to get out the oil. But my source about this was Olivier Coussy, who recently died very young, but he was the expert in France about oil reservoirs, and he was also very skilled mathematical physicist. So my source about this is that one. So imagine to have a solid fluid mixture with pores interconnected, and imagine to have a shock wave traveling inside this material. Now, the model is this one. You have an homogenized procedure, and at a microscopic level you have solid and fluid, but and all these are standard. For instance, the true density of the solid is the mass of the solid divided by the volume really occupied by the solid, but you have the apparent mass density, which is obtained dividing the mass of the material times the volume of the elementary representative volume. So with this homogenization procedure, you may describe the kinematics in this way. You have two domains, reference domain for one continuum and the Eulerian placement domain, the map from one domain to the other, which is placing every material particle in the actual Eulerian reference, and all fields from one domain to the other can be transported using trivial composition. So these are trivial ideas which one needs to consider if you want to use a variational principle for attacking the problem. I will go quickly through this, but maybe I can let you catch the idea simply. You need an action, and you need a set of fields like key we have introduced here, and motion is a time evolution of these fields. Okay, so when you try to estimate the minimum of action, you need to have a fixed domain and a given set of functions defined in this domain. Now the problem arises. If you have a shock wave, so a discontinuity surface traveling in your continuous system, where are you integrating? If you integrate in Eulerian space, then your domain is varying with time, and your problem is to find how it is varying with time. So it is very difficult to calculate the first variation of this animal. And this is a technical difficulty of relevance. Then there is another technical difficulty of relevance. You have a material particle which is crossing a surface. So if you follow this material particle, the velocity may be discontinuous. However, the trajectory is continuous. So you have the serious problem of finding the appropriate Hadamard conditions to be imposed on the discontinuity surface. Okay, so you need to say that placements are continuous. You have the gradient of placement on one side and the gradient of placement on the other side, which are well defined. So the gradients of these quantities, space gradients, are well defined, and also velocities on both sides are well defined. However, these gradients and these velocities may be discontinuous. Okay, now here I hope that nobody will pull my leg when I tell you that we need four-dimensional space-time description of this motion. So you introduce space-time, and you have a map from a configuration four-dimensional domain to an Eulerian four-dimensional domain. Instead of using the standard approach you find in relativity, as we don't have any particular velocity, we keep the first three components of dimension space and the fourth component of dimension time, and this is leading to some difficulties, because inner products here become impossible, so you need to work with duals. Okay, this is for motivating the fact that instead of using R3, we studied a little bit the differential geometry from Rn to Rn. We considered invertible continuous mapping, which are differentiable almost everywhere except on one surface. And we have found some transformations of the fields defined on the first domain and on the second, and their divergence, and the jump of the normals. This F is the gradient of this field, J is the determinant of this gradient, and zeta ball is the composed of the field from one domain to the other. Now, with these conditions, we get the appropriate kinematical informations which are necessary. Okay, so this is here it is described the four-dimensional the four-dimensional embedding, remark that time is fixed, so different motions are not changing time, and the four-dimensional gradient is the space gradient and time gradient, and the divergence in 4 dimensions, you need a field which has 4 indices at the end of type space, of the type space-time. But all these, with all this, you should be rather familiar. So at the end, this decomposition becomes possible. The gradient of this displacement actually is the old space gradient, and you have here velocity which appears. And this, for instance, that divergence is showing you at the fourth component that the divergence transformation formula, that the material derivative Eulerian is the natural correspondent of the partial derivative with respect to time in the Lagrangian reference configuration. Okay, so these technicalities are needed for attacking the problem as follows. You introduce a fictive configuration. So you have the prototype of your surface. Then you introduce a first map which is transporting your fictive configuration onto Eulerian space. Then you have a key 1 star which is spotting the first material, the first component of your body, which is the material particle which is placed in the first given position. And then you have this for every constituent of your system. So if you have a pure fluid, you have only 0 and 1. If you have a porous medium of a solid matrix with a fluid, you have 0, 1, and 2, and if you have P components, you have P of them. Okay. The idea is the following. You know perfectly, it is a redundant description of the motion. You know where every material particle is placed if you know all of these placements. And you know also where the discontinuity surface is located. So this trick is needed if you want to have a set of functions defined on a fixed domain to describe the kinematics of your system. Of course, this is it is redundant, because you may describe via a diffeomorphism, you could introduce a double star, a different fictive configuration, and you get another possible representation of the same motion. However, another type theorem will give us exactly the right number of equations based on physical content of the Lagrangian. I will tell you more precisely this immediately. If you have an action, this is written in the book of Landau, if you have an action of the type integral or on a domain of a density of Lagrangian defined in terms of the fields we have introduced, Euler-Lagrange equations are for bulk on the left and jump conditions are given on the right. So in this frame, you immediately have the evolution equations you need. However, Sorry?
How do you include the dissipative term in this formula?
For the moment, there is no dissipation, and you want to study Rankine-Hugoniot condition, the advancement of the shock wave without dissipation. Then you may say that the first variation of A star is equal to the first variation of a dissipation potential, and then you add, instead of equal 0, you have a dissipation there, and okay, so for the moment, Rayleigh, Hamilton, Rayleigh plays it by hand, right. Okay, but this action star actually has a physical meaning only when you represent by means of an action defined on the Eulerian configuration. So you are not considering the most general Lagrangian density. You are considering this particular Lagrangian in which only some of the gradients of all introduced fields appear, a particular combination of them, okay? As a consequence of this particular choice, so we remark that the number of independent fields is P, is not P plus 1, okay? When you use this particular action, then the P plus 1 vector equations show the particular property that only P of them are independent. So when you consider bulk equations and the particular form of Lagrangian introduced, redundant description of the motion does not affect the situation, and you get one equation which is depending on the others. So this is not a true problem. However, the jump conditions, in a painful way, you can verify that P of them are independent, but the P plus 1 condition, which is a vector condition, has one scalar component which is independent and two tangential components which are depending on the others. So this general scheme gives you exactly the extra condition which is required for finding how the discontinuity surface is moving in your system. Now, the details are boring, but with some calculations, and you will recognize this form starting from the Lagrangian, which appears very often in mathematical physics, the extra condition, that one which is needed to describe the motion of the free-moving boundary, is in terms of the introduced Lagrangian given in this form. Now, what is interesting, and I will stop after having given some comments about this. What is interesting is that if you project space, the standard equation bulk, you get balance of force for every component of your system. You get balance of force at the jump condition and the extra evolution equation there. Okay, I skip. Balance of mass is verified trivially for the system, I stop showing you, telling you that the calculations we have performed up to now to apply this general scheme have led us to the following result. The extra equation we have written, when applied to the case of pure fluid, directly gives formula 15, which is from the standard books cited there. That is, you have the velocity on the left, u1, the velocity on the right, u2 of your fluid. Density on the left, density of the right, ρ1, ρ2. A standard, this gamma is the standard coefficient for energy, the constitutive equation, the state equation for the fluids. S is the speed of shock wave. So my remark here is that in standard books in fluid dynamics, you get 15 using a magic trick. Which is the magic trick? You postulate first equation, balance of mass at the surface. Second equation, balance of force. Now everybody knows that in bulk equations, balance of mass and balance of force imply balance of energy, mechanical energy, if you have no heat transmission, anything. For a strange reason, Rankine needed to postulate independently, third equation, balance of energy at the surface. So, if you have bulk equations, balance of mass and balance of energy, then, balance of mass and balance of force, then balance of energy depends on the first two. However, if you have a surface discontinuity, balance of energy is not implied by balance of mass and balance of force. To get the classical 15, the speed of shock wave in a pure fluid, you need to manipulate in a rather simple but complex way the three equations I have written before, and after a while, and having killed one spurious solution which has no physical meaning, you get this expression, which is the result of standard application of the solution of a second order equation, algebraic one, right? So the minus sign there is killed for physical reasons. Instead, if you consider the more general variational approach I was quickly and brutally presenting before, that last equation I have shown you directly gives you this equation, and you don't have any spurious solution to be killed on basis of physical reasonings. So what I hope, but I didn't dare to show you, is that with this reasoning we can produce the shock wave condition in a porous medium which is not available in the literature, simply applying that equation. Okay? So thank you for your patience.